1 minute ago, the ground beneath Japan moved in a way no living scientist had ever witnessed. At 2:46 p.m. on March 11, 2011, a magnitude 9.0 earthquake tore through the seafloor 72 kilometers off the coast of the Oshika Peninsula. The shaking lasted 6 agonizing minutes, an eternity in seismic terms. Buildings swayed like grass across Tokyo, 373 kilometers away, their steel frames groaning under forces that exceeded every engineering specification. Then the ocean pulled back, exposing mudflats and fishing boats stranded on wet sand, revealing the seafloor in places where water had stood for centuries. What returned was not water, it was a wall. Witnesses described a sound like distant thunder growing louder, then the horizon rising as if the sea itself had tilted. The waves swept inland at 700 kilometers per hour, faster than any evacuation could hope to outrun. It traveled up to 10 kilometers from the coast, obliterating everything in its path. Was this simply the world's next disaster, or the first warning of something far more dangerous still unfolding beneath the Pacific? Could a thin layer of clay deep beneath the ocean floor explain why the earthquake defied every scientific prediction? And what does this tell us about the next megaquake waiting to strike? The early warning system detected the tremor within seconds of the first seismic waves reaching the mainland. Alarms screamed across every coastal prefecture, from Chiba to Aomori, piercing the afternoon calm with mechanical urgency. But the system had made a fatal error in its calculations. It predicted waves no higher than 3 meters, a height the coastal barriers were designed to withstand. Many towns had 3 minutes or less to evacuate from the moment the shaking stopped. In some villages, sirens were drowned out by the roar of collapsing buildings and snapping power lines. Relay towers damaged by the shaking failed to transmit warnings to outlying districts. Communication networks fractured in the crucial minutes when every second mattered. Half the population never heard a warning. For the elderly in low-lying districts, there was no time to reach high ground. For those in hospitals or care facilities, evacuation was physically impossible. The tsunami arrived, traveling at 700 kilometers per hour across the open ocean, slowing only slightly as it approached the shallow coastal shelf. In Miyako, waves crested at 40.5 meters, the height of a 12-story building, dwarfing every structure in their path. Entire neighborhoods were swept clean in seconds, leaving only foundations and debris fields where homes had stood minutes before. More than 18,000 people died or vanished. The underestimation of wave height proved catastrophic in ways no one had prepared for. Evacuation routes designed for smaller tsunamis led directly into the path of the surge. But the waves were only the beginning. 10-meter seawalls built to withstand the worst historical tsunamis were overtopped instantly, water cascading over the top like waterfalls in reverse. Reinforced concrete barriers designed to dissipate wave energy shattered like ceramic, their rebar cores exposed and twisted. In Kamaishi, a massive breakwater designed to protect the harbor, one of the deepest and most expensive tsunami defenses ever constructed, was obliterated within seconds. The force of the water bent steel girders like wire and uprooted foundations anchored 30 meters deep into bedrock. Critical infrastructure collapsed in cascading sequence, each failure triggering the next. Flooded substations plunged entire prefectures into darkness as circuit breakers tripped and transformers exploded. Backup generators failed when seawater poured into reactor basements, flooding the very systems designed to prevent meltdown. Hospitals lost power mid-surgery, forcing doctors to operate by flashlight. Cell towers toppled under the combined assault of shaking and flooding. GPS systems went silent as ground stations lost power. Shinkansen bullet trains froze on their tracks as all rail service across northern Japan shut down within minutes. Highways buckled where the ground beneath them liquefied. Bridges twisted as their support columns shifted. Ports filled with wreckage and shipping containers stacked like playing cards, blocking all maritime access. The smell of seawater, fuel oil, and dust hung in the air for days. What broke Japan was not just the water. It was the speed, it was the totality, and it was the realization that every defense had failed at once. Beneath the Pacific, something impossible had occurred. A 500-kilometer segment of the Japan Trench ruptured in just over 2 minutes. The seabed shifted vertically by as much as 50 meters in places, an amount so extreme it violated every standard model of subduction zone behavior. Scientists had long assumed that shallow portions of the fault near the trench were weak and incapable of storing enough stress to produce catastrophic slip. The 2011 earthquake shattered that assumption. The rupture didn't occur as a single smooth event. Instead, multiple fault patches labeled S1, S2, and S3 by seismologists failed in rapid succession. Each segment released energy in bursts, propagating the rupture faster than typical earthquakes. The shallow slip near the trench was so massive, it produced what researchers described as a kinematic shock. This extreme displacement of the seafloor generated the tsunami that devastated the coast. But no one knew why the fault had slipped so violently. Within 13 months of the earthquake, the research vessel Chikyu sailed from Shimizu port on an unprecedented mission. The Japan Trench Fast Drilling Project, known as JFAST, aimed to drill nearly 7,000 meters beneath the ocean surface to reach the fault zone itself and sample it before the heat signature from the earthquake dissipated completely. Time was critical. Theoretical calculations showed that measurements needed to begin within 2 years to detect the residual friction heat. The team faced extreme technical challenges at every step. Water depth alone exceeded 6,900 meters, deeper than almost any previous scientific drilling expedition. The drilling string stretched over 7,700 meters from ship to seafloor, setting records for the longest string ever deployed. Equipment designed for shallower operations had to be modified. Hydraulic pressure at those depths crushed components. Weather delays forced suspensions of drilling. Each meter took immense effort. What they found rewrote the science of megathrust earthquakes. Core samples revealed a thin layer of highly sheared clay, less than 5 meters thick, a zone so narrow it seemed impossible that it alone could account for the massive slip. The clay showed penetrative, scaly fabric and localized slip surfaces, evidence of repeated past earthquakes. Laboratory analysis identified it as smectite, a volcanic sediment altered over millennia into an ultra-low friction material. The friction coefficient measured just 0.08, comparable to Teflon on ice. This clay acted as a geological lubricant, allowing the plates to slide with almost no resistance. Temperature sensors embedded in the borehole at 820 meters below the seafloor recorded residual heat from the earthquake, with estimates suggesting the fault reached approximately 700 degrees Celsius during rupture. Some measurements indicated temperatures as high as 500 degrees in localized zones. Thermal pressurization explained the rest. As friction heated the fault, pore water trapped in the sediment turned to steam, dramatically reducing resistance even further. Dr. Harold Tobin, co-chief scientist on the expedition, called the findings the smoking gun. The discovery forced a global rethinking of tsunami hazards at other subduction zones. If a thin layer of weak clay could enable 50 meters slip, similar conditions might exist elsewhere along the Pacific Rim. And the fault had not finished speaking. A fishing boat from Kesennuma washed ashore on the Oregon coast 2 years after the tsunami. It was one piece of a debris field containing approximately 1.5 million tons of wreckage carried into the open Pacific by the retreating waves. Debris continued landing on beaches across the United States and Canada for years. Over 280 Japanese marine species survived the transoceanic journey, hitchhiking on floating wreckage. Some became invasive along the west coast. Traces of radioactive isotopes from Fukushima were detected in the debris and in Pacific currents. The ocean had connected 2 continents with disaster. More than 200,000 people remain in temporary housing over a decade after the earthquake. Survivors report chronic PTSD, depression, and anxiety. Children startle at loud noises. Adults fear water and darkness. Suicide rates in affected regions rose more than 20% in the years following the disaster. Elderly survivors already isolated before the quake found themselves cut off entirely as entire communities dissolved. The economic cost exceeded $300 billion, making it the most expensive natural disaster in recorded history. But the true cost may have been trust.
Leaked reactor logs from Fukushima Daiichi tell a story of concealment and miscalculation that continues to haunt Japan's nuclear industry. Engineers knew within hours that 3 reactor cores were overheating beyond control, their temperatures climbing past every safety threshold. Handwritten plant logs show radiation levels rising to numbers that would normally be unthinkable, measurements taken not inside the reactor itself, but in control rooms and offices. Internal communications obtained years later show heated debates over whether to vent radioactive steam or risk complete meltdown, with pressure mounting on both the containment vessels and the decision-makers. Yet public statements from Tokyo Electric Power Company and government officials consistently downplayed the severity of what was unfolding. TEPCO was later found to have been instructed not to use the phrase core meltdown in any public communication until 2 months after it had occurred, despite engineers suspecting meltdown had begun within the first day. Data from the Speedy Radiation Monitoring Network was delayed or withheld from local officials. Detailed radiation maps produced by U.S. military aircraft were not forwarded to the Nuclear Safety Commission for days. The exclusion zone around Fukushima now spans over 1,150 square kilometers, an area larger than Hong Kong. Radioactive water continues leaking into the Pacific daily, despite extensive efforts to contain it. Critical contamination data was withheld from local officials and international agencies during the first weeks of the crisis, when evacuation decisions were most urgent. All 3 reactor cores largely melted within the first 3 days, fuel rods fully exposed, and molten material pooling at the bottom of containment vessels. The cleanup is expected to take 30 to 40 years and cost well over $500 billion. Some villages will never be inhabited again.
Across the Pacific, the earthquake's influence spread like a slow contagion through interconnected fault systems. Magnitude 6.0 or greater earthquakes increased nearly 300% around the Pacific Basin in the years following 2011, a spike that defied statistical chance. Fault systems, once thought isolated and independent, began showing signs of agitation and accelerated movement. Clusters of seismic activity were recorded from the Aleutian Islands in Alaska to the subduction zones along the Chilean coast, thousands of kilometers from the Tohoku rupture. The Japan Trench had transferred stress across vast distances of interconnected faults. Dr. Yuko Kato at the Japan Meteorological Agency warned that the Pacific Ring of Fire, the 40,000-kilometer chain of subduction zones and volcanic arcs encircling the Pacific Ocean, had entered a heightened alert state. Seismologists now estimate a 70% probability of a future megaquake in the Nankai Trough, a subduction zone southwest of the 2011 rupture that runs parallel to Japan's heavily populated southern coast. The stress unleashed by the Tohoku earthquake continues migrating through the crust at rates measured in centimeters per year. Global seismic risk maps are being redrawn based on new understandings of how stress propagates. Studies using Coulomb's stress transfer models show that 78% of aftershocks occurred in areas where the main shock increased stress on surrounding faults by at least 0.3 bars. The correlation is too strong to be coincidental. The pattern is unmistakable. The earthquake didn't just release energy, it redistributed it across the entire western Pacific margin, loading adjacent fault segments closer to their breaking points. Some aftershocks traveled extraordinary distances. Large earthquakes struck in regions thousands of kilometers from the epicenter, triggered by seismic waves propagating through the Earth's crust. The sensitive connection between fault systems around the Pacific Rim became undeniable. What happens in one subduction zone can influence another half a world away. The 2011 event was not an isolated rupture, but part of a much larger system of tectonic interactions that scientists are only beginning to understand. And the system remains active. Research published in Nature Geoscience shows that seismicity close to the rupture surface can shut down for centuries following a megaquake, while a much larger surrounding zone remains activated for decades. A ring of enhanced seismic activity formed around the Tohoku rupture, extending up to 10 times larger than the original fault area. Rate and state friction models explain how stress transfer continues long after the main shock, slowly loading adjacent fault segments closer to failure. The Tohoku earthquake was not a one-time event, it was a trigger. Deep-sea drilling at other Pacific subduction zones has revealed similar conditions.
Smectite-rich clays have been found in fault zones from the Cascadia subduction zone off the Pacific Northwest to the Nankai Trough off southern Japan. The discovery that weak, low-friction sediments are common along many plate boundaries suggests that the potential for extreme shallow slip and devastating tsunamis may be far more widespread than previously believed. Scientists cannot predict when the next megaquake will strike, but they now know where to look. Artificial intelligence analysis of microearthquakes recorded after 2011 identified thousands of previously undetected seismic events. These swarms cluster along newly recognized ring faults encircling active calderas and along subduction zones. The analysis revealed structures that could focus future earthquakes and amplify their impact. Each new dataset refines the picture, but uncertainty remains vast. Forecasting the precise location and timing of a magnitude 9.0 earthquake remains beyond current scientific capability. What scientists do know is troubling. The Tohoku earthquake moved Japan approximately 2.4 meters eastward and shifted Earth's axis by approximately 16.5 centimeters. The rupture altered the length of a day by about 1.8 microseconds. Vertical displacement of the seafloor changed ocean depths across a region the size of California. GPS measurements show that portions of the seafloor continue to move, driven by post-seismic deformation and afterslip along the plate boundary. The Earth is still settling from the shock. Evacuation drills continue across Japan. Tsunami barriers are being rebuilt higher and stronger. Nuclear reactor safety protocols have been overhauled. Early warning systems have been upgraded. Yet all of these measures are responses to the last disaster, not predictions of the next. The thin layer of clay discovered by JFAST remains in place along the Japan Trench. The Pacific Plate continues its relentless march westward at 8 to 9 centimeters per year. Stress accumulates. Faults bend. Rocks compress. Somewhere along the Ring of Fire, another fault is nearing its breaking point. The 2011 Tohoku earthquake remains an active geological warning. The stress it unleashed continues to shape the Pacific Basin. Aftershocks still rattle northeastern Japan. Radioactive water still flows into the ocean. Survivors still live in temporary housing. The scientific data is clear. Megaquakes of this scale are not isolated incidents, but part of a long, interconnected cycle of tectonic violence that spans centuries. The next rupture is not a question of if, but where and when. What are we willing to risk ignoring?